For this lesson, we're going to be taking a look at something known as the sine law. We're continuing with our unit on trigonometry, but the big difference that we have taking place here is that we're now going to be dealing with triangles that don't have right angles in them. I've tried to portray that here with a triangle that is relatively clear. It's relatively clear that there is no right angle here. You might look at this vertex C and maybe think that that's a right angle, but I can assure you that it's not. And obviously A and B are not right angles. So everything that we've done in trigonometry up until this point, which has hinged around the idea of sine, cosine, and tangent. So that is using the mnemonic SOHCAHTOA to help us remember that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Unfortunately, all of this requires a right angle triangle. And so if I don't have that, then I can't just use sine or cosine or tangent. So that's obviously going to be a problem if that's all we had to work with. But it turns out you can manipulate this triangle a bit, and one way you manipulate it is you can actually break this triangle up. So if I drop a perpendicular line here, you can see that what I've done is I've created two right angle triangles. And by doing that, I can actually use right angle trigonometry. In this case, for the sine law, I focus on using the sine ratio, sine theta, and I come up with these different ratios. Now, I'm not going to derive that here. I'm going to do that at the end of the lesson. I'm going to come back and I'm actually going to show the derivation of these. But for now, you're just going to have to take what I'm saying, which is that the sine law comes in two different formats. And what the sine law does is it relates the angle in each vertex. So in this case, it relates the sine of the angle in this vertex A to the length of the side opposite, which is small letter a. And if we take a look at A, B, and C, whether it's vertex or side, you should notice that there's something they have in common, which is that the largest angle, which is quite obviously C, goes along with the largest side. The smallest angle, which is B, goes with the smallest side, and the middle side and the middle angle go together. And you can see that's the arrangement we have here. These ratios can be flipped over and it still applies, and that's just like if I said 3 over 4 is equal to 6 over 8 is equal to 12 over 24. Those are all true statements. They're not all true statements. I've messed them up, haven't I? I messed up this last one. Let's try that again. What am I doing here? Let's say 9 over 12. That works a little bit better. Now this is a true statement. Apologies for that. I can flip this over and it's still true. 4 over 3 is the same as 8 over 6 is the same as 12 over 9. These two larger fractions still reduce to 4 over 3. So all of these are true. Well, that's the same thing is true here. If these three ratios are equal to each other, then the reciprocals of these three ratios are equal to each other. Now, when do you use these? You have a choice to make here. Which one should I make use of? And the decision on when to use them really depends on what it is you're trying to solve for. In general, if I had x over 6 equals 11 over 17, most people will find that easier to solve. If you're comfortable with cross multiplying, it doesn't really matter. So let's say I had 6 over x equals 17 over 11. For most people, if you're comfortable with cross multiplying, it doesn't matter. But for some people, they might not be super comfortable with cross multiplying, or they might look at this and realize, oh, the easiest thing to do here is just to multiply both sides by 6. Whereas when you have this one, that it's never going to be that easy. If you cross multiply, it works out just fine. But if you try any other technique, you're going to have to add multiple steps. So in general, this is not a right or wrong, but this is a suggestion. If you are trying to solve for the angle, okay, so in that case that's A, B, or C. If you're trying to solve for the angle A, B, or C, then use this form where the capitals are in the top, sine of the angles. If you are trying to solve for a side, then that would be lowercase a, lowercase b, lowercase c. Then you're going to want this form to solve for a side. But as I said, it doesn't matter so long as your algebra skills are sharp enough, you can use either form and it will be fine. So as I mentioned, I'm not going to derive this yet, so I'm going to skip over these blue pages and come back to them. Let's go ahead and actually start with a practical example. You can see I've got a triangle here. There are many things that we're going to do that are similar to solving, again, this word solve. Find the value of x or values of x that make this true. So first of all, I notice that I'm solving for a side. So I'm going to use the form a over sine a equals b over sine b equals c over sine c. And the reason I'm doing that is because I'm solving for a side. Now I'm actually going to fill these things in. So the side length a is actually what I've described as the variable x. The sine of the angle a turns out to be the sine of the angle 45 degrees. The side b, as you can see here, I didn't fill anything in for the side b, so I'm just going to leave that as b. And the angle b also is not filled in. Now that's not to say we won't use it, but I'm just writing what I'm given right now. And the side C is 4. The angle for C is 37 degrees, so that's going to be the sine of 37 degrees. Now we take a look and say, do I have enough information to be able to solve for what I want? In this case, I do have enough information because I want the x. I have sine 45 degrees, I have the 4, and I have the 37. So I can take this piece and this piece, and I can bring them together, and I can write a single new equation which I can solve. X over the sine of 45 degrees is equal to 4 over the sine of 37 degrees. And now that I have those two, that cross multiplication, which is something we do a lot of here, I have x times sine 37 degrees is equal to 4 times the sine of 45 degrees. And we put the variable or the number in front of the trigonometric ratio. To get x all by itself, I'm going to divide both sides by sine 37. So sine 45 degrees over sine 37 degrees. The reason why I do this all algebraically to start is because I would like to put this all into my calculator in one pass. So I'm going to do that now. 4 sine 45 divided by sine 37. I'm fortunate I've got a calculator that lets me put that in fairly directly as is written. And so that's approximately equal to, from my calculator, I have 4.69983, which is far more decimal places than I need. I think I'll round this to one decimal place, so that would be equal to 4.7, and that's approximately equal to. And if we take a look back at my original, I actually have the answer here waiting for us, and that is approximately 4.7, which is correct. Now I just want to revisit something I said, which is after I filled out what I was given, I then asked myself, do I have enough information to go ahead and solve? Which I did. But if I didn't have enough information, don't forget that there may be other things that you could find here. For example, the angle B. That's pretty easy to find because I know the other two angles. So I could actually say that the angle B plus the angle 45 degrees plus the angle 37 degrees is equal to 180 degrees. That's the angle sum theorem. And so from that, I could easily find what the angle B is equal to. So that's just in case, something to keep in mind. So here we were looking for a side, and we chose the form of the sine law that allows us to easily find a side. Now, in this question, we are looking for the angle. We're looking for the angle theta. And so that means I'm going to use the form sine A over A is equal to sine B over B is equal to sine C over C. So now you notice I put the angles along with the sine of each angle in the numerator, and the side lengths are in the denominator. Now, I'm just going to, again, to mix things up a little bit, I don't want you to think that you're always going to have triangles that are labeled ABC. Sometimes they will be labeled for you, and it is very poor form to relabel a triangle because the question itself is referring to those labels. So I'm actually going to label this as PQR, and I'm going to modify this to represent that. So I'm still going to do it alphabetically if possible. So instead of A, the first letter of my triangle is capital P, and that's going to be over the side P. And then I have Q over the side Q, and I have the sine of the angle R over the side R. And now, just like before, I'm going to fill in what I know and what I'm looking for. So sine of capital P is actually the sine of 52 degrees over lowercase p is the side 100. Sine of capital Q, that's theta. So that's sine of theta. That's what I want. And the side is 75 opposite to that. That's the side Q across from the angle Q. Sine of the angle R is not given to me, and the side length R is not given to me. And just like our previous question, if we had to, we could calculate this R. Actually, we couldn't. We don't actually know two angles, so this is all we have to work with for now. What are we interested in? We're obviously interested in this theta, and we know that one, we know that one, we know that one. So the equation I can use is made up of those two. So I end up with, I'm just going to rewrite it, sine 52 degrees over 100 is equal to sine of theta over 75. Cross multiply, I end up with 100 sine theta is equal to 75 sine 52 degrees. I divide by 100 this time. I'm not going to divide by sine theta. I actually want sine theta all by itself. And I get 75 sine, not very nicely written, sine 52 degrees divided by 100. And my preference is algebra. You could change this into a number right now. And that's particularly okay if you keep it in your calculator. But I'm going to go one step further, which is I'm going to say that theta, if sine theta equals this thing, which is just going to work out to be a number, then theta itself is the inverse sine of this thing, 75 sine 52 degrees over 100. And I've done that because I want to be prepared to do the whole thing in my calculator if I can. Now I'm actually going to do this in two steps, just so you can see. So I'm actually going to do this part first, the part in the bracket. And even though I'm going to write it down here, I'm actually going to keep all these digits in my calculator. So I'm going to do 75 sine of 52, and I'm going to divide that by 100. And I end up with the sine inverse of 0.5910. But I'm actually not, I'm keeping many more digits in my calculator. So that's approximate now. But I'm keeping many more digits in my calculator because now I'm actually going to take the inverse sine of the answer from my calculator, and I ended up with approximately 36, and I'm going to round that to one decimal, so 36.2. Don't forget, this is an angle, which means the units are degrees. And just to confirm that, here is the answer I had calculated in advance, and it is 36.2 degrees. Okay, so now I think this is our last example. We've been asked to solve for the side length y. And so since this one is adding some additional complexity, I'm just going to go ahead and I'm going to label it in the way that you're probably more comfortable with. I'm looking for a side of y. So before I do that, I'm going to write out, I'm looking for side lengths. So I'm going to use the form a over sine a equals b over sine b equals c over sine c. Okay, so let's see what I've got here. Do I have the side length a? I do. It's down here. It's 100. Do I have the angle a? I do. It's 52 degrees. So that's a good start. Equals. B. Do I have the side b? I do not have the side b, so I just label that as b. Sine of the angle b. Do I have that? Yes, I do. That's the sine of 48 degrees. Equals c. The side c is the letter y, the variable y. That's what I'm looking for. And the angle c, well, that's unfortunately unknown. So this is what I want, but I don't have this. This is good. I've got two pieces of the ratio. I've got both pieces of the ratio over here. I could solve for b if I wanted to, but I don't actually want b. What I really wish I had was the angle c. And as we've talked about before, that's actually very doable. When you have two of the angles, I can just say that the angle c plus 48 degrees plus 52 degrees is equal to 180 degrees from the angle sum theorem. So that's the angle c plus 100 degrees is equal to 180 degrees. The angle c is equal to 80 degrees. And so now I've calculated this one. I'm going to use these two together, and I end up with 100 over the sine of 52 degrees is equal to y over the sine of 80 degrees. Now, since I'm using this number that I calculated, it's worth it just to make a, take a second look at this, make sure we've calculated this correctly. I know it's just simple arithmetic. So 48 plus 52, yes, that is indeed 100. 180 minus 100 is equal to 80. So I'm pretty confident about this. I go ahead and cross multiply. I end up with y sine 52 degrees is equal to 100 sine 80 degrees. I write y isolated, so that means I divide both sides by sine 52 degrees. And the reason I do that is so that I can get my answer in one step on my calculator if possible. I'm not trying to be fancy by doing this. I'm just trying to minimize any potential errors. So 100 sine 80, and I'm going to divide that by the sine of 52, and I end up with y equals 124.9738977, so 39. Okay, now, and that would round, that's rounded already, and I'm going to round that to one decimal place. And because this 7 is going to cause this 9 to round to a 0 plus a 1, this actually rounds to 125.0. You have to include that 0.0. And before I check my answer, let's just see whether or not that's even remotely reasonable. I've got a side length here of 100. And so 52 degrees went with 100. This angle was 80 degrees. Notice that this 80 degrees, it's not really reflected very well in the triangle. You shouldn't make assumptions about the drawings you're provided that may or may not be to scale. But 80 degrees is the largest angle, which means it should have the largest side. So if 52 degrees is the middle angle, the middle side is 100, 125 as the largest angle, or the largest side, that seems to make sense. So, and we should finish with a therefore statement here, because I didn't put in my units yet. So 125.0 centimeters. And I check my answer there, and I've got an angle for theta. Obviously, I kept something from the previous question not realizing that I was changing what I was solving for there. I'm pretty confident that that is actually correct. Now, and that makes me want to go back and just double check an answer here. And you can see I actually did make a mistake here. No, that's 36.2 degrees. That's okay. What about this one? And this had no units, so I was okay with the way this was written as well. I was just wondering whether or not I missed a concluding statement in any of those problems. Okay, I think that's it for sine law. There are the homework questions that go along with this. Now I'm just going to take another moment in this video lesson, and I'm actually going to go through the derivation of sine law. So if you're interested in that, we're going to go back to those pages we skipped over before. Okay, and so you can see this is what I mentioned before. Triangle ABC. Originally the triangle has no right angles in it. So the way I introduce a right angle is I drop this vertical line, and this is known as an altitude, something we covered in the geometry section of this course. And so by doing this, I've actually created two right triangles. And so what we're going to do is we're going to use the trigonometry on each right triangle to make some sort of relationship here. Now you still have to do this. You can't just do this any way you want to. And actually, I'm only going to show you part of this, because to do this properly, you actually have to do two of these triangles this way. You have to do this twice. I'm only going to do it once. So in this case, I'm going to focus on this angle A and this angle B, because the angle C has been cut in two, or actually it hasn't been cut in half, but it's been cut into two different pieces. And for the same reason, I'm not going to be interested in this side C, because it's been split at this point where the altitude drops down. So instead, I'm focusing on the A's and B's. Now, since this is a right triangle over here, and it is the sine law, so what is the sine of capital A? The sine of capital A is, if we remember from SOHCAHTOA, the sine of capital A, the sine of an angle, is equal to opposite over hypotenuse. So for this angle A, where is my opposite? It's here. And where is my hypotenuse? It's here. I'm going to change the color for these ones. I'll change them to red for when we go through those. But let's focus on this blue one first. So sine of A is equal to opposite over hypotenuse. Sine of A is equal to opposite, which is H, over the hypotenuse, which is B. Now for the red one, which is going to be this angle and this side, so these are the two in the red side of the triangle. For the angle B, where is the opposite side? Well, it's still here. And where's the hypotenuse? It's up here, across from the right angle. So the sine of the angle B is H divided by A. But that's kind of weird. That's not like the sine law yet, because here I have the angle A with the side B, the angle B with the side A. But now what I'm going to do is I'm going to rewrite these. This one, I'm going to rewrite this as, I'm going to cross multiply, or multiply both sides by B. I end up with B sine A is equal to H. And here, I'm going to multiply, and I end up with A sine B is equal to H. And H is equal to H. So now let me bring these together by saying set H equal to H. And so we end up with B sine A is equal to A sine B. I'm going to divide both sides by B. Actually, I'm going to divide both sides by AB. And the reason I do that, I'm allowed to do that, I can divide both sides by AB. On this left side, B divides out with B. And I end up with sine A over A. On this right side, A divides out with A. And I end up with sine B divided by B. And then you can, with another altitude, So if we were to draw another altitude, it's tough with the way I've drawn this triangle, but if we were to do that with another altitude, we then end up showing, so I'm just going to say here, can also show, we could get a relationship like this, which is that sine A over A equals sine C over C. But if sine A over A equals sine C over C, and sine A over A equals sine B over B, then that means that all of them must be equal to each other, and we end up with the sine law in general. And I believe that's all I've got on this next page. Yeah, it's just a nicer version of that exact same thing. So there you go. You can see that the derivation of the sine law, you can see this is not particularly difficult or involved. It's just using right-angled trigonometry and making some insightful decisions on what you work on and why, the idea of why did we make these two right triangles. Okay, that's it for this lesson on, I think I'll, just for some people who've jumped ahead here looking for the homework, and so that's it for this lesson on the sine law.